In this video, let's talk about regression. Right. Uh, so this is again an example that we're taking from our textbook. It's um, it's just a very simple data set with like 20 data points. So we've got like for every data point you have both the horizontal coordinate x and the vertical coordinate, which is y. Right. So we have 20. So that's like 1, 2, 3, 4. 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 data points, right? And then we have another 10 data points. So we have 20 data points in total. So the goal is to actually come up with a curve that can actually best fit all those 20 data points, right? And so regression is one of those curve fitting techniques. So it's one of those techniques, right? And um, in fact, there are several curve fitting techniques or surface fitting techniques, um, and regression is one of those popular techniques for curve fitting or surface fitting. And so in this video, let's try to solve the regression problem by using our own linear system solver that's called matlab19, right? Um, so the first thing we're going to do is to actually try to import the data. Let's try to import the data into our workspace. Um, so we have matlab19, that's our own linear system solver that's based upon the steepest descent algorithm. We have been using this algorithm before to solve linear systems, right? In a previous video, we were using this particular function to solve linear systems. Um, and then this function is going to call our own matrix multiplication function that's called a matlab. So we have both functions here. And then the data set that I was just showing you, the 20 data points, uh, those data points are actually inside of this text file called regression.dat. It's just a normal text file. Um, so if we go to the Windows Explorer and then take a look at what's actually on the desktop, so we have regression, right? And this text file can be opened by just using Notepad, right? Where's my Notepad? Oh, yeah, that's Notepad, right? So it's just a bunch of numbers, right? So for every point we have like two numbers, x and y. So we have like 20 numbers in total. But the lines are not kind of truncated correctly because the file was generated on a Mac, so the new line symbol is not displayed correctly on the Notepad. But once we have imported the data into Matlab, we will be able to actually see the correct dimension of it. Alright, so now let's try to load the data. We'll do this thing in the command window first, and then we will copy all those commands into a script later on. So let's do a d equals to. So when we did the car examples, all the data were in the Excel format, right? It's a Word Excel. It's a Microsoft Excel format, right? And we were basically just using if we go to the Home tab, we have a button that's called Import Data. We're basically just using the import wizard to actually import those Excel files, right? But here, this data file is a lot simpler. It's not an Excel spreadsheet. It's basically just a text file, right? For this kind of file, we have a simpler way for loading them into Matlab. It's called load, right? And that's a Matlab intrinsic function. So, and here it's actually telling me how to actually use this particular function. It's called load with the file name, and the file name is basically just a string. And then the string for our case, it's going to be regression.dat, right? That's our string. So as soon as we have typed in this particular command, we're going to get the dimension of d. That's 2 times 20 doubles. So it's 2 row, 20 columns. That's the dimension of d, right? And then why it's 2 rows, right? Because every data point has like 2 coordinates, x and y. So that's the 2 rows. The first row is x, the second row is y. And then why it has like 20 columns, right? Because we have 20 points. So every column corresponds to 1 data point, right? And then the next thing we might want to do is to just maybe take a look at all the data. Right? Let's make a plot of it. Let's just use the plot D, the first row. Um, maybe it's not a good idea to operate on D directly. Let's assign the two different rows into two vectors. So x is gonna equal to the first row of D. Right? If I just type like that, so that's the row index. That's 1, right? And then for the column index, it's gonna be a range, but the starting and ending index are left unspecified. So Matlab is going to take the default value. So the starting index is going to be 1, and ending index is going to be the last column, which is 20, right? But for later calculations, we don't really want x to be a row vector. If we just do this thing, x is going to be a row vector with 20 columns, right? So let's transpose it. So x is going to be a column vector, right? So x is going to be a 20 by 1 double, right? 20 rows, 1 column. So and then we're going to do the same thing for the second row. That's going to be y, and then we're going to also transpose it, right? So now we have x, y, right? So now let's make a plot. Let's just plot x and y, and then we're going to use symbol that's red cross, and then marker size. Let's use like 10, right? So it's easier to see the data points. For some reason, it's taking longer than expected to plot. So that's the 20 data points, right? So horizontal axis, vertical axis, right? And then for every data point, we have its horizontal coordinate, and then the vertical coordinate, the corresponding vertical coordinate. So that's all the 20 data points, right? And then our goal is to actually come up with a curve that's gonna best fit all those data points, right? What does it mean by best fit, right? It means it actually has a very specific mathematical definition about what's actually the best fit. So depending upon how you actually define what's actually the best fit, you can come up with different kinds of curve fitting algorithms. And the regression is based upon one specific definition of what does it mean by a best fit, right? So what's going to be the curve that we're going to try to construct? We're going to try to construct a curve that's a kth degree polynomial. So the curve that we're going to try to put together is called y equals to a0 plus a1x plus some intermediate term up to like ak times a to the kth power, right? So that's the curve that we'll try to construct. So x and y are the horizontal and the vertical coordinates of different data points, right? And then a0, a1 up to ak are the coefficients that we'll try to actually determine. We don't really know what a actually is, right? We have no idea what a actually, but we'll try to actually determine what's actually the best set of choices for the a's, right? So that the curve that we come up with is going to be the best fit to all the data points, right? And then we have n data points given by xi, yi, right? I goes from like 1 to 2 to n. And then for this particular specific example that we are looking at now, it's 20 data points. So n equals to 20. N equals to 20. 1 to 2 up to like 20, right? So we have 20 data points. And for every data point, we can compute a y based upon the x, right? So for x1, we can stick x1 into the right-hand side and then compute a prediction of y, right? And then we can compare that prediction y with the actual y1, for example, right? And then that's exactly what's actually been doing here. What we are doing here, right? So on the right-hand side, we are sticking xi into the right-hand side, and then we come up with a prediction of y. And then we use the actual yi, to subtract that prediction, right? And then we square the difference, right? We square the difference, and then do a summation over all the data points. If we have like 20 data points, then this is a summation over 20 data points. So that's going to be the residual. So capital R is going to be the residual, right? So the goal is to actually find, if we are doing a linear regression, then the goal is to actually minimize R. And R is defined in terms of this kind of square, right? The square of the difference in the y-axis. right? That's R. So how do we actually minimize R for different choices of A, right? So what we want to find is the best choice of A so that capital R is minimized, right? So how do we actually do that, right? If you have studied calculus before, the correct way for finding the minima is actually to take a derivative with respect to those A's, right? So if we have like a k, this many parameters, we take a derivative with respect to each of the A's, right? Take a partial derivative. And this partial derivative can be actually calculated analytically based upon this particular definition of R. Right? And then we're going to see that it's going to equal to, so it's going to give us how many equations it's going to give. So if we set the derivative, if we set the first order derivative to 0, right? So that's the standard way for finding the minima of extreme, any kind of extreme in calculus, right? You compute the first order derivative and then set the derivative to 0, right? So how many equations do we have? We have k unknown variables, k plus 1 actually. So it's starting from a0, right? So it ends with k. So it's actually k plus 1 equations, right? And then all those equations can be reorganized. It basically just involves some algebra, right? We have to sort of be patient when we actually work out the algorithm, when we actually work out the algebra. It's not difficult, but it takes some time to actually to work it through, right? And then we can try to come up with the correct equation. So that's a matrix multiplied with this vector of unknowns. That's a0 to ak equals to, this is another vector which can be computed from the data points. So this matrix can be computed from the all the horizontal axis of all the 20 data points, right? And then this vector can be computed from both the horizontal and the vertical axis of the data points, right? And then uh, we can do some simplifications. So basically this equation can be expressed as this equation multiplied this equation. No, this matrix can be expressed as this matrix multiplied with this matrix, right? And then this particular vector can be expressed as this matrix multiplied this vector, right? So if you don't believe me, you can try to validate it, right? You can try to validate the equations, right? And then just by examination, we see that this matrix and this matrix are identical to each other. They are the same matrix actually. So you can cancel out these two matrices on both sides of the equation. And then the equation that we end up with is this equation. And that's the equation that we have to solve, right? So this matrix can be constructed by just using the horizontal axis of all the data points, the 20 data points, right? And then that's the unknown vector. And this vector is composed of the actual y's for all the data points. If we have like 20 data points, then we have like 20 numbers on it, right? So the equation that we have to solve is x times a equals to y, and that's a linear system, right? And we have to and we can actually use our own linear system solver to actually solve it, right? So let's try to write a script. Right? So home no no new new script, and let's write a new script, right? So this is going to be E5 actually, E5 for our course, right? And then this is going to be regression. Right? So E5 is really short. It's just composed of this particular one exercise, right? So it's unlike all the previous exercises we have done, which has lots of codes involved, right? But this one it just has like a one or two codes actually. Right? Let's save this file. Let's save it. Let's call it my regression. Save it. Right. So we have a few lines of code that's kind of we have already written here, right? So that's for loading the data. Let's just use the command history window to copy over those lines, right? So hold down the shift key and then select all of them and then copy them over, right? And then we can just paste them, right? And then maybe let's try to come up with a specific figure, right? Figure 1. This is figure 1. And then if we want to start over again, let's do COF. I think COF is the correct command for clear out all the existing figures in the figure window. Right? If you haven't used the COF before, let's just type help COF in the command window and see if so clear current figure, right? So okay, that's good. And then let's call our linear. Let's construct the X matrix and the Y vector first. The Y vector is already there, right? But what's going to be our X matrix, right? What's going to be our X matrix? Right? X matrix is going to look like that. So each row actually corresponds to one data point, right? So if we have like 20 data points, then we should have like 20 rows. So n goes from like so x1, x2, xn, right? So and then how many columns do we have depends upon what's actually the order of the polynomial that we're gonna try to construct, right? So suppose we set k equals to 1, right? And then it's just gonna be the first order. It's just a straight line, right? It's the first order. So it's just gonna have like 2 columns. The first column is all composed of 1. And then the second column is just going to be x1, x2 up to like xn, right? Because k is set to 1, right? So x1 to the first power, that's x1. x2 to the first power, it's x2. So if we choose k to be 1, then we're trying to construct a straight line. So y equals to a0 plus a1 x, right? And then x is gonna go from like x1 to x20, and then y goes from y1 to y20. So if we just choose k equals to 1, then the problem becomes really simple. It's the capital X matrix has just 2 columns, right? And that's really easy to construct. So let's try to construct capital X. Capital X is gonna equal to the first column is gonna be all 1, right? And then the dimension vector is gonna be the same as x, right? And then we use a comma to separate the different columns of the capital X matrix, right? And then x is going to be this small x is going to be the second column, and that's capital X, right? And then we can use our own linear systems over that we have worked on in E3, right? In E3 we have our linear system. We did the linear system solution, right? So that's called Matlab solve, right? And then the input it's going to take is the A matrix, but in our case, the A matrix is actually the X matrix here, right? So if you sort of forgot about the notation, so it's X times A equals to Y. So A is the unknown variable that we are trying to solve for, right? X is the known matrix, right? And then when we were actually doing this when we're writing this Matlab solve, this particular function, A is supposed to be the matrix, right? And then Y is the actual observed vector. LR is the so-called learning rate, and NI is the total number of iterations that the steepest descent algorithm is going to take, right? It's going to take this many steps in the direction of the gradient, basically, right? So let's use this particular function, and then let's try to solve our problem. So A is going to equal to Matlab solve, right? So the first input x, the second input y, and then the learning rate, let's just use 0.01, and then let's iterate like 10,000 iterations, right? And then that's going to be our A. We're going to get our A, right? Now, once we have the A, we can construct our curve. We can construct our curve now, right? Our curve is just y equals to a0 plus a1 x, right? But now x and y are both supposed to be continuous, right? But if we want to make a plot of it, of this line, we have to sort of either discretize it somehow, or by using the fplot function of Matlab. So Matlab is going to discretize it automatically for us, right? We can do it either way. So let's just explicitly discretize it, right? So let's construct the horizontal axis. Let's call it x-axis, right? X-axis is going to be a link space, and then we're going to use min of x vector to range to max of x vector, right? And then let's just give it like 100 data points or something, right? It doesn't have to be too many, as long as it looks like a line. Then and it's actually a straight line, right? So in principle, you just need like 2 data points. That's kind of enough, but nevertheless, let's still try to construct like a 100 data points. So y is going to equal to a0, a0, a0 is going to be what? A0 is going to be the first element of the a vector, and a1 is going to be the second element of the a vector, right? So it's going to be a1, that's the first element, time plus xx a2, right? And then let's hold on to the plot, and then plot xx y, and then let's just use blue straight line, right? So now let's execute this piece of code. So that's our best fit straight line to go through all the data points, right? And we have been using our own. Maybe I should make it access tight. Access tight, right? So that's a linear regression, right? With just the reason that it's called linear is not because we are just fitting to the first order of x. It's because all the a's, right? It's because all the a's, the relation, this right hand side is a linear function of all the a's, right? It's not a linear function of x, right? If you want to include x squared and up to like x to the sort of k's power, and k is larger than or equal to 2, then that's a nonlinear function in x, right? But it's a linear function in a's, or the a0, a1, it's a linear function, and that's the a's is unknown, right? Because x and y are given, but a's are not unknown. So with respect to the unknown a's, it's a linear function. So that's why it's called linear regression, right? But you can actually replace all the x with some other function that you pick, right? It doesn't have to be those polynomials. Here it's just the x to the 0th power time, and then x to the first power, and then up to the x to the k's power. It doesn't have to be all polynomials. You can pick any kind of, for example, Gaussian. You can pick some Gaussians that's kind of located at some places, right? And then you're gonna do another kind of regression. So you can choose. You can choose what's gonna be the building block. What's gonna be the kind of a basis polynomials that you are trying to sort of combine together using some kind of optimal choice of coefficients, right? Okay, so it looks like our code actually worked, right? So it gave us the correct figure. So we have come up with the let's look at what's actually the numbers inside of a vector. It's supposed to have just the 2 numbers. So a0 is like 41 something, right? It's 41 7 4 9 6 9 8, and then the a1 is 3.7366, right? So that's our own implementation of linear regression, right? So, but for this kind of a specific problem, for this particular specific, Matlab also provides a very straightforward way for you to actually solve it, to solve for a, right? So let's call it a1. No, a1 is a bad name. Let's call it aa, right? Aa may, what you can do is to use this operator that's called backslash, right? So that's your x vector, that's your x matrix, and then that's the y vector, and then you put a backslash between them, and then solve for it, right? So in this case, it's going to give us identical results basically. So A was computed using our own linear systems over matlab19, and then AA is computed by using Matlab's backslash operator, right? And the results are identical, at least to the significant digits displayed in here, displayed on the command window, right? So one of the things that we mentioned when we actually were working on the matlab19 is that we don't really like this particular fixed number of iterations, right? So the reason is because we don't really know how to actually pick this number, right? If it's too big, then we might be just wasting computing time. We are just waiting idly to do some kind of unnecessary calculations. But if it's too small, maybe the steepest descent algorithm hasn't converged yet, right? So it hasn't converged to the true solution, correct solution yet. So how do we actually so when we're writing this particular Matlab solve function, this 10,000 was just an arbitrarily big number that we provide, right? And then we try different numbers, right? And see if we increase this number, see if the result actually changes significantly or not, right? If it doesn't change significantly, which means that the number of iterations is probably sufficient to get to convergence, right? But now we have better understanding of we know a little bit more about the Matlab workflow, flow control, Matlab flow control, right? So maybe we can actually come up with a better criterion for us to actually decide how many iterations we want to run for the steep descent algorithm, right? So here we are actually using a for loop, right? And so the number of iterations is like fixed, right? But now we know another way of writing the loops. That's called the while loop, right? The while loop, and the while loop is different from the for loop in the sense that the while loop allows us to specify a condition, which is gonna allow us to actually specify what's gonna be the condition for continuing the execution of the body of the loop, basically, right? Or the condition for stopping the iterations, right? And then we reverse that condition for stopping the iterations. Then that's gonna give us the condition for keep iterating, right? So can we actually come up with a good criterion or good conditional that's gonna allow us to automatically determine what's gonna be what's gonna be a criterion for the appropriate criterion for keep iterating, right? So there are two choices, right? The first thing that you might think of is probably based upon the error vector, right? So y pred subtract y, that's kind of a quantification. So the error vector is kind of a quantification between the actual observed y, that's the vertical coordinates of the 20 data points, right? And the model predicted y, right? So basically the error is basically just this thing, right? So the stuff that's inside of the square bracket, right? That's the observed y, and then that's the predicted y. The whole thing in the parentheses is the predicted y, right? So, but in here it's the sort of observed y subtract predicted y, right? But because you have a square here, so it doesn't really matter which one subtract which one. So you can use the predicted y subtract the observed y also. It doesn't really matter too much, right? So if you define error this way, it's also fine, right? So the first thing that comes to mind is probably just to use this error vector to determine if we have reached convergence, right? So if the error vector is kind of too small, very small, right, compared to the size of y, for example, then we consider we have reached convergence, right? But the problem is that we are not really solving the linear system exactly, right? The linear system is not satisfied exactly, right? So if we look at our curve, this straight line doesn't actually pass through every data point explicitly, right? It doesn't actually pass through any of those data points exactly, right? Which means what? Which means this error may never reach zero, even at the best fit, right? At the best fit, even at the best fit, this linear system is not satisfied exactly, right? This linear system is not satisfied exactly. So this equal to, even for the best fit, this equal to doesn't really hold. So the error could be quite large, even at the best fit, right? Even if you have reached the best a values, right? You have found the best a values, the error could be still quite big, right? And sometimes if you are trying to sort of fit some very irregular data points, some of the data points could be very way above the line, and some of the data points could be way below the line, and then you try to come up with a compromise that might lie in the middle, right? So the error could be quite big, right? So if we try to use the error or the size of the error, some kind of norm of the error, then it may not give us the correct convergence criteria, and the loop could go on forever, right? In that case, we have a dead loop. We have a dead loop, infinite loop, right? So it's never gonna stop, right? And then a second observation is to use the g vector, right? why do we actually want to use the G vector, right? Because the amount of change to the X vector, the solution, in our case it's A vector, right? It's the unknown vector, right? The amount of change to the unknown vector is LR, that's a constant, times the G vector, right? That's the amount of change that we apply to our estimates of the unknown vector, right? So we change it a little bit every time, every iteration, right? And eventually we can actually accumulate lots of differences, right? So for every iteration, the amount of change that we apply to the X vector or the A vector that we are solving for the regression problem here is just this vector, and that's kind of linearly proportional to the G vector. And in fact, for our problem, the G is exactly the gradient. Actually, it's a vector, so it's actually pointing into the direction of steepest increase of the objective function, basically, right? And in our case, that's the residual. The objective function is pretty much just the residual, right? It's this residual, right? So can we actually build our conditional or build our criterion for continuing the iteration based upon the size of G, right? Why do we want to do that, right? Why do we want to do that? Don't forget. So this is actually taking the derivative of the residual with respect to each of the A's, right? So that's exactly the gradient, right? That's exactly the gradient. So this thing that's written here, if we put them into a vector, that's exactly the same as the G vector that we're computing here, right? If you don't know why we do a transpose times the error vector is going to give us the G vector, we can talk about that in a separate video, right? It's a basic result in linear algebra, basically, right? But it's a very simple result, but it's a kind of very deep, right? So it allows us to actually understand the gradient vector in a deeper way, right? But you can sort of see at the location of the optimal A's, all the components, all the elements inside of the gradient vector is supposed to be equal to 1, is supposed to be equal to 0, right? So which means what? Which means the length of the gradient vector at the optimal A's, optimal A values, is supposed to be very close to 0, right? And this is a condition that can be actually used for us to actually stop the iterations, right? So if the gradient vector, the length of the gradient vector is much smaller than the gradient vector that we started with, the length of the gradient vector that we started with, which means that it's very close to 0 now, right? Then we can stop the iteration, right? That's exactly the criterion that we are using in calculus for finding the optimal values, right? So let's try to implement that. And see if we can actually come up with a reasonable implementation. Let's write the conditionals first, right? Don't forget, G is actually a vector, right? It's not really a number. So how do we actually quantify the length of a vector? And Matlab actually provides a quite convenient function that's called a norm. If you haven't used the norm function before, you can type help norm, right? Right, so it allows us to actually quantify the length of a vector in several different ways. That's like the default case, right? That's the 2 norm of x, right? So 2 norm means what? 2 norm just means you're gonna square each element inside of the x vector and then do a summation of it, and then you square root the summation. Right? That's sort of a very popular norm that we have been that's used very widely, right? So let's just use this norm vector, a norm function. So the norm of G, if the norm of G is larger than a certain criterion, then we can sort of keep iterating, right? What might be a good criterion, right? What might be a criterion? But what might be the value that we can choose for this location, right? What might be a good choice? What might be a good choice, right? But before we worry about that, let's make sure that let's give it some kind of placeholder. Let's call it G0. Let's say, right? But as soon as you finish writing this line, you're gonna see that you're getting a orange wiggle line underneath the G, which means that Matlab has detected some syntax error. So the variable G might be used before it is defined, right? So why? Why? Because Matlab is going to execute each of the lines sequentially. It's going to do this line and then do this line, and then it's going to come to this line. It's going to compute G. It's going to compute the norm of G. But when Matlab reached this line, G hadn't been defined yet. G was computed later on inside of the body of the loop, right? So how do we actually fix that? How do we actually fix that? Let's just move these three lines outside of the loop, right? Let's just cut it. So we're gonna do the first iteration outside of this while loop. So these calculations, these three lines are gonna be the first iteration or part of the first iteration, right? And then once we have finished the first iteration, we're gonna have a G, right? And then at this point we can actually compute its norm. Let's just call it G0 equals to the norm of G, right? So now we have something to compare with. So that's sort of the norm that we started with, right? That's the sort of the norm that we started with. So as we actually progress towards the optimal A value, the gradient is gonna reduce, right? So as we get closer to the correct A value, the norm of G is gonna reduce, right? It's gonna reduce. So as long as it's larger than a certain fraction of G0, the gradient that we started with, we're gonna keep iterating. So let's use G0 divided by 1e10, right? That's like a huge number, right? So if the norm is like still larger than G0 divided by like a 10 billion, then we're gonna keep iterating, right? So the first thing that we're gonna do to keep iterating is to update x first based upon the G, right? And then the next thing we're gonna do is to actually compute the y, and then the area vector, and then recompute the G, right? So we're gonna copy those three lines over into the body of the loop again, right? Control I is gonna smart indent, I think. Right. So that's gonna be our new function, right? That's gonna be our new matlab function, right? So let's and then we're not gonna need ni anymore, right? Because ni is not used anymore. So let's get rid of ni as the input. Learning rate is still needed, right? So let's keep that. Let's save the function, right? And then let's go back to my regression. And then let's change the code to matlab solve. Let's comment out this line. And then we're gonna replace it with a new call to our new function that's gonna have like just the three inputs. Let's copy it and then paste it over. Right. Okay, so now let's rerun this code and see if we can recover the correct result. Yeah, it looks like it's still correct. Right. And then if we look at A, is it still the same as AA? Yeah, it's still the same as AA, I think. Right. At least to the display the significant digits, right? So that's gonna be E5 basically, right? So, but you can play with this particular code, right? So for now we're just fitting like one term. We're just fitting like to the first order term, right? So it's gonna be just a straight line, right? Suppose we wanna sort of fit a second order polynomial to it, so you can add another column to the X matrix, right? So suppose we want to do y equal to a0 plus a1x plus a2x squared, right? And then all you have to do is to just add another column to the X matrix, right? So the first column is still just going to be ones. The second column is still going to be the X vector, but the next column is going to be X dot square, right? Dot hat 2. Right, that's going to be the next vector. And then if you want to include the cubic term, that's x dot hat 3, right? The third component-wise power, cubic power, right? So you can try different adding more and more terms. So if you add more and more terms, your curve is not going to be a straight line anymore, right? As soon as you add the second order term, it's going to have some kind of curvature to it. Right. If you go above the second order, then you have it's not a straight line. It's going to be some kind of curve, right? The fit to the data are going to be better, right? Because you are allowing more freedom to fit those data points, right? The curve doesn't have to be a straight line. Can bend around to fit those data points, right? So the curve can do more to actually fit those data points. You're going to reduce the misfit. You're going to reduce the residual, right? But usually you want to sort of use the simplest form of the curve, right? So if you can actually achieve a 80% reduction of the residual by using a straight line, then you probably don't want to go to like a second order or third order curve, right? If going to the second order, third order only gives you like a 5% of reduction in the residual, then it's probably not a good idea to actually use more terms, right? Because that's going to increase the complexity of your model, regression model, right? So it's a bad idea to do that, right? You can play with that. So you can play with that. You can play with this particular code, right? And now it's for the example that we are actually looking at here, it's got just one independent variable, that's x, right? What if you have like multiple independent variables, right? What if? So this is example 8.9 of our textbook. But if you look at the next one, you have example 8.10. It's called a multiple regression analysis. See? So now you have more than one independent variable. So y, the observation y, depends upon multiple independent variables, x1, x2, and x3. So now the subscript 1, 2, and 3 is not an indication about the data points. It's actually different independent variables, right? And that's the data points. So how many data points we have? It's still like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 26 data points, right? So 26 data points. And every data point is actually a 4-dimensional data point. So it's got like three independent, three axes on x, right? So x1, x2, and x3. So it's got three independent variables and then one dependent variable, right? So every data point is determined by these three x's, right? And then one y, right? x1, x2, and x3 are variable name, right? It's not, so the subscript is not for indicating the data ID, the data point ID, right? So but for the first data point, you're gonna have this value. So x1, x2, x3 is known, right? And then y1 is also known. The first for y. So again, you have to solve for beta. So beta 0, beta 1, beta 2. Again, you can convert that into a linear system, and then try to solve that linear system, right? And see if you are gonna discover more problems, right? And for this particular data set, you may have problems with our own linear systems over, right? If you still try to actually use this particular function to solve for this particular problem, you may have some difficulties, right? But see if you can actually work out the difficulties, right? But the idea is kind of similar, right? You construct a linear system and then try to actually solve for the beta vector, right? The idea is kind of similar, right? So basically, we can actually solve regression problems by solving linear systems, right? And once we have a robust functional routine for solving linear systems, essentially we can actually solve any kind of regression problems, right? So here for this particular multiple variable thing, you still have like this is still the linear part, right? That's so it's basically just a surface, right? 4-dimensional surface. But these terms are second order terms, right? x1 times x2, x1 times x3, right? x2 times x3, x1 square, x2 square, x3 square. That's like second order terms, right? So it's not exactly a plane. It's actually a curved surface, right? So you're trying to actually fit a curved surface through those 26 data points, right? And then for this kind of a 3-dimensional thing, 3-dimensional independent variables, you can also generalize. It doesn't have to be polynomials, right? So here it's still polynomials. You can generalize to other kinds of functions, right? So maybe it's a good time for me to actually stop this particular video, right? So, but for the exercise E5, that's E5. So if you wanna email me your codes, that's the two codes that you want to email me: my regression and my link solve, my matmal isn't changed any somehow, so it's still gonna be the same as E3, right? But my link solve is kind of different from E3, so you have to email me these two codes, right? So this is a very short exercise.